Hello, today we're going to solve a fairly difficult integral which we can easily solve using some tricks and a nice technique very similar to one we've already practiced quite a few times on the channel here. So I'll do probably a couple of videos on similar integrals and how you can solve and recognize this trick easily. So first of all, maybe a hint on how to solve this would be this x to the power of pi, which isn't really a nice expression, and so maybe we're looking at a more continuous version, right? So what if we consider the general case, the integral from 0 to 1 of x to the power of a minus 1 divided by log of x dx. And then we would evaluate that at a equals pi if we wanted our integral, right? So what could we do with this? First of all, for those who know the trick already, you could apply Feynman's trick easily. And you'd get a really nice result quickly, but today we're going to do something else, which is a little more clean in this case. Now, what are we going to do? We're going to write this integrand as an evaluation of a different integrand. So mainly we're going to have x to the power of a divided by log of x, x to the power of, let's say, y, divided by log of x, evaluated from 0 to a. So notice that we've not changed anything. If we were to evaluate this like we would with any other integral, let's say that this was a solution, then we would get x to the power of a minus 1, since x to the power of 0 is 1, right? And the log of x is just a constant with respect to y, so that doesn't actually do anything, right? So it's important that we plug in these values for y. Now, so we're assuming this is from some kind of integral, right? An integral is an antiderivative, so we should take the derivative of this function with respect to y, right? Now, it's an exponential function, so the derivative rules for that is we're going to get a log of the base, and the base in this case is x. So we're going to get the integral from 0 to 1 of the integral from 0 to a and then x to the power of y. We took the derivative, so we're going to have log of the base, which is x, divided by log of x dx, dy, because this is an integral in y, dx, right? So now we've got this double integral, and obviously we can just get rid of these log of x's, right? And what we'll do now is the main idea of this trick. So we're going to switch the variables of integration. So we're going to switch this to the integral from 0 to a times the integral from 0 to 1 of x to the power of y dx dy. And this integral in x is really simple. It's just going to give us, let's see, the integral from 0 to a, and then we're going to have to evaluate that. So the evaluation from x of x to the power of y plus 1 divided by y plus 1 evaluated from 0 to 1 dy. And so at this point we're going to evaluate this with regard to x, right? So x to the power of y plus 1 is just 1, and we're going to get the integral from 0 to a of 1 over y plus 1 dy, since x evaluated at 0 is just 0. And this is just a standard integral, which is log of y plus 1 evaluated from 0 to a, and this is equal to log of a plus 1. Also recall log of 1 is just 0. So nice, we've got this solution to our integral just in one long equation of integrals and double integrals as well. So maybe let's just write down our final answer for the integral from 0 to 1 of x to the power of pi minus 1 divided by log of x dx. That would be equal to log of pi plus 1, and that's it. But maybe for some people it's even nicer to have this general formula for x to the power of a minus 1. Now, for those of you who want to try this with differentiating under the integral, it's perfectly possible. I think it's just quite nice as well because we've got this minus sign incorporated into the integral, which is kind of nice. Now, maybe something else. So right now I'm going to do a similar integral, an even more general one, from 0 to 1 of x to the power of a minus x to the power of b, divided by log of x. dx. And my challenge to you is to solve this integral using the technique we just did. So just writing this out as an evaluation and just switching the bounds of integration. Now we're going to do this for fun using another really nice technique for integrals, which is Feynman's integration. So how will we do that? Well, we're going to write this as a function of f and of a and b. So this is a multivariable function which we're going to use to solve the integral. So first of all, maybe take the partial of f with respect to a, for example. So the partial of f with respect to a is equal to the integral from 0 to 1 of x to the power of a log of x divided by log of x dx. And again, we can just get rid of these log of x's, and we've got this very simple integral, which we can immediately see is 1 over a plus 1, just by a similar argument as the last integral. Okay, so taking the partial with respect to b of f, we would just get the integral from 0 to 1, and then we would just have the exact same process as before, except we're going to get a minus sign and of course x to the power of b dx. And this would be equal to minus 1 divided by b plus 1. But now we could use these derivatives with respect to a and b to find antiderivatives to get the function, right? So in this case, for example, we would see something like f of a comma b is equal to the log of a plus 1, as we already saw in the last example as well. But then with the constant, but it has to be constant with respect to a. So it could be some function g of b, right? So that's also possible, since it's just constant if you were to derive it with respect to a. And then secondly, the same holds for this function, right? So we would get f of a comma b would be equal to minus log of b plus 1 plus some function, let's say h of a. But from this it's very clear that our function f of a and b would just be equal to log of a plus 1 minus log of b plus 1. So in other words, our constant function g of b is going to be equal to minus log b plus 1, and our constant function h of a is going to be equal to log of a plus 1. And so we just get this function for a and b, which is equal to log of a plus 1 minus log of b plus 1, which is equal to log of a plus 1 divided by b plus 1. And that is our function in the end. So our integral from 0 to 1 of x to the power of a minus x to the power of b divided by log of x dx is equal to log of a plus 1 divided by b plus 1, and that is our final answer. And now, of course, the challenge is do it with the other technique. And also, the second challenge was to do it with was to do this integral using Feynman's technique. So I hope you enjoyed this video. I think we saw some fairly interesting tricks, both Feynman's trick and a double integral trick. And if you want me to, definitely let me know. I'll do some more of these similar kind of tricks, both using double integrals, maybe triple integrals, and just let me know whatever you want to see on the channel. Thank you so much for watching. I hope this was clear. Till next time, thank you so much for watching.